Many times in physics, we discover things in theory before we prove them in practice. Back in 1784, a man named John Michell made a prediction that sounded strange at the time. By then, science had a solid understanding of gravity, at least from Newton's perspective. We knew that if we threw a ball into the air, it would fall back down, accelerating at a rate that depends on the mass of the Earth, or whatever planet we're on. But Michel observed something intriguing. He noted that if a star, like the Sun, were at least 500 times more massive, a flashlight pointing upwards would emit light, but the light would be pulled back down by the star's intense gravity, never escaping. This hypothetical object, which Michel called a dark star, wouldn't emit any light because the escape velocity would be so great that not even the fastest thing in the universe, light itself, could break free. This was the first recorded idea of what we now call a black hole. Michel's concept of an object that couldn't emit light was groundbreaking for his time. And remember, this was 1784, long before Einstein was born. We didn't understand relativity yet. Maxwell's equations describing light hadn't been published, and we weren't even sure if light was a wave or a particle. Today, we know that Michel was right. There are objects like what he called dark stars, now known as black holes. However, he was right for the wrong reasons. Let's fast forward 121 years to 1905. In that year, Einstein published a paper that introduced a revolutionary idea in physics, special relativity. This theory was built on two core principles. The first, the laws of physics are the same no matter what frame of reference you're in, whether you're on a spaceship traveling close to the speed of light or sitting at home watching TV. The laws don't change. The second, and perhaps the most mind-boggling, the speed of light is constant for all observers. This means that if you're moving at 90% of the speed of light and you turn on a flashlight, you'll still measure the light from that flashlight traveling at the speed of light, exactly the same as if you were standing still. Strange, right? But why does this matter? These two postulates of special relativity might seem simple, but they have massive implications. The fact that the speed of light is constant for all observers means that space and time cannot be constant. One consequence of this is that the faster you travel, the slower time passes for you compared to someone standing still. Distance also shrinks. This means that space and time are no longer two separate things. They have to work together as a single entity. But special relativity had some problems, especially when it came to gravity and acceleration, which are ironically the key elements in understanding black holes. Fortunately, in 1915, Einstein introduced a new theory, general relativity. This theory builds upon special relativity and applies it to the entire universe, hence the term general. It solved the previous issues and allowed us to describe the universe and gravity in ways never before possible. One of the key tools used to describe gravity in this new framework is Einstein's field equation. This equation is so complex that even Einstein didn't think anyone would ever solve it. That was until a few months later when a physicist named Karl Schwarzschild found a solution. Yes, a tricky name. This solution had a peculiar outcome. If you took a certain amount of mass and compressed it into a small enough volume, the escape velocity at the surface of this object would be equal to the speed of light. Does that sound familiar? It should, because it echoes Michel's dark star idea. But Schwarzschild's solution had something even stranger, a literal point of strangeness. When all of the mass is confined within a specific volume, known as the Schwarzschild radius, not only does the escape velocity reach the speed of light, but all the mass of the object seems to collapse into a single point at the center. This point is what we now call a singularity, a point of infinite density at the center of a black hole. This is where things get really strange. In most artistic depictions of black holes, we typically see a dark sphere occupying a lot of space. But this leads to one of the most common misconceptions. Black holes don't have a surface. You can't land on them. What we're actually seeing is the event horizon, a kind of boundary. Beyond this point, neither mass nor light can escape. It's precisely at the event horizon that escape velocity equals the speed of light, which is the fastest anything can travel in the universe. Once something crosses the event horizon, it's lost forever to the outside universe. But the strange things happening near a black hole don't stop there. Imagine what would happen to someone falling into one. Yes, they die. But let's focus on what happens before that for the sake of curiosity. What if we had an indestructible person falling into a black hole? For any distant observer like us, safely watching from a spaceship far away, the gravitational field near the event horizon would make time appear to slow down. This is a direct result of time dilation, a phenomenon predicted by relativity. The closer the person gets to the event horizon, the slower we would see time pass for them. In fact, we did never actually see them cross the event horizon, because time would seem to stretch out infinitely as they approach it. But that's not the only thing that changes. The light emitted or reflected by the person would also be affected. As time appears to slow down, the light waves stretch out, resulting in a redshift, meaning the light shifts toward the red end of the spectrum. The falling person would gradually appear redder and dimmer until eventually the light fades completely. That would be the last signal we'd ever receive, the final trace that this person ever existed. But wait. We're not done talking about black holes yet. There's one detail that people often overlook. Since black holes have mass, it's actually possible to orbit them, just like you can orbit planets, stars, or even galaxies. In fact, there's a specific distance from the event horizon called the photon sphere. Any photon or particle of light traveling at this distance would be trapped in a perfect orbit around the black hole without falling in. This leads to some fascinating effects, like being able to see the back of your own head while looking straight ahead, because the light from behind you could complete a full orbit and reach your eyes. Despite these intriguing effects, black holes aren't as dangerous as we often imagine. They're massive objects, yes, but so are planets, stars, and galaxies. You can orbit a black hole safely. In fact, if the Sun were to suddenly be replaced by a black hole of the same mass, Earth wouldn't feel any gravitational difference. We'd keep orbiting it as usual. Of course, we'd lose sunlight, which would be catastrophic. But gravitationally speaking, nothing would change. And of course, this wouldn't be a science discussion if we didn't briefly acknowledge how much we still don't know. Humanity likes to believe we've figured everything out, but that's not really the case. Take singularities for example. When solutions to Einstein's field equations predicted singularities, points of infinite density, people were shocked. How could something in the real world have infinite density? It didn't make sense then, and it still doesn't now. We're still trying to figure that out. It's unclear whether singularities truly exist, or if they're just a quirk of our incomplete theories. Many scientists believe that the next major breakthrough in physics will involve uniting general relativity with quantum mechanics. And a lot of hope is placed on this new theory explaining away singularities altogether. We're living in an incredible time for science. Even though the mystery of singularities persists, black holes themselves are no longer just theoretical. We actually captured the first ever image of a black hole, and it looked exactly as predicted after 100 years of theorizing. It's amazing to witness the confirmation of the work of so many scientists who never even lived to see it. So, while we can appreciate the beauty of these cosmic phenomena from a distance, let's all agree to stay far away from black holes in real life, just to be safe. Thanks for watching, and I see you in the next video.